Hello, welcome to my talk. Thanks everybody for staying this long, coming to this last slot of the day, I think, or well, the last before the closing keynote. So I want to talk about concurrency models on the JVM. This first slide shows the whole, already shows like the big stretch this talk is about. It's about concurrency models. So it's kind of, it's kind of abstract. We're going to talk about different approaches, different principles maybe underlying those. But I have a little code example. You see there's a little GitHub repository. So we're going to talk about concurrency models, but we're also going to look at a lot of code. Because I'm a very pragmatic guy, I don't like to talk about the abstract only. I want to look at code and want to see how these concepts actually are reflected in the code that I have to write in the end. But before we start, I'm also a bit of a book nerd. I like books, but books and concurrency, that doesn't go well together, right? A book we read from start to end, from the first page to the end. So that's very sequential, you'd think. But actually, there's an interesting book by my favorite author, Arno Schmidt. If you speak German, if you are familiar with the German language, you should definitely read something by this author. He's absolutely great. And this book is called Zettelstraum, and it has, well, it's probably difficult to see because it's also, the book is like 800 pages thick, and it's copies of his typewriter pages. And it has 3 columns because he tells 3 stories, or he has 3 threads of action going on in parallel. So parallel, I can tell you from reading this book, I actually haven't read the whole book, but I can tell you from reading this book that reading parallel stuff is hard. And I think when we look at programs that are parallel and we reason about it, how things happen, this is also hard. Because there's another book, it's also a very funny book, it's called, well, it's French, I forget the title, 100,000 milliards de poèmes. So it's 100,000 billion poems. So you'd think that's also a very thick book. It's not, though. But all the pages, it's a 14-line sonnet, and it's 10 of them. It's 10 14-line sonnets, and the pages are cut. So you don't browse it page by page, you can browse every single line. So you can combine these to 10 to the power of 14 poems. So now if you think about how a computer would concurrently execute your stuff, just say it's one single core, like I'm a single reader, and you have, say, you have 10 threads with 14 instructions. How does the computer actually execute these? In which order? Well, it seems there are 10 to the power of 14 possibilities for that, right? He can combine it in any possible manner. So to know what's actually going on in a concurrent program is rather difficult. To test it, the way we think about test coverage is that every line of code is covered and has been gone through in the execution of the program. But really, in a multi-threaded world, you would have to test, to have complete test coverage, you would really have to test all the possible combinations. Well, maybe not. It kind of works without, but I just want to sort of open your mind. Well, I think I want to make the point that this is an interesting problem. Concurrency is interesting, it's worth thinking about. Luckily, we don't have to do it by hand, we have the computer. So, because it's a bit abstract and about models, I want you to stay motivated. I want to put up this claim. I'm gonna claim that the Java world needs a new concurrency model. That's a bold claim. I said threads are rubbish. We want to have something on top of that. So this is something, maybe after this talk over beer, you can discuss that. And I'm going to give you some material for this. So why do I not like threads? What are the problems with threads? I think there are 2 fundamental problems. The first one is efficiency, or rather the lack of efficiency. The thread model, it's pretty old. I don't even know when it was discovered or introduced. We had multiple processes, and then somebody had a great idea and said, oh, processes, they're just too heavyweight. I cannot just always switch between processes. I want to have something within the process. I want something that's in the same address space as the process, a lightweight process. And hence, the threads were born. But at that time, that was at the time where we had single core machines. So this is trying to visualize how computers work with lumberjacks. So we have a single core machine, and the processor core is this chainsaw there. And we have a number of threads. This is the lumberjacks, and they have some work to do, the logs. So Obviously, we all know how multi-threading works. It's time sharing, right? So one of the lumberjacks gets the chainsaw, can work on his log, and then at some point he has to pass it on to somebody else. And then this person or this thread gets the CPU. This lumberjack gets the chainsaw, the thread gets the CPU. It's actually not a stupid model. It leads to, well, this is how we get a good utilization of the chainsaw, right? We don't want the chainsaw lying around. We want the chainsaw to be shared. It's an expensive resource, so it's good if they share it. Of course, if you pass on the chainsaw to another lumberjack, there's some overhead to that, right? You have to, maybe you have some protective gear you have to wear, and there's a context switch going on. So nowadays also, it actually looks different. We have multi-core CPUs. It's not just one core. And all this is about having very many tasks that we want to work on. It's this whole thing is especially interesting if you think about high concurrency, if you think about servers that have thousands of connections, for example. So if you have that, this becomes ineffective. You have a number of cores and you want to switch them between 10,000 lumberjacks, and you can easily imagine that the overhead of the context switch becomes so relevant that it's not an optimal model anymore. And also it seems weird that each of these lumberjacks just has one log to work on. Right? I have this one log and I have to wait for one of these chainsaws to be assigned to me, and then it starts, I have to wear the protective gear and start working, but then I have to pass the chainsaw on before I get my work finished. And then when the one log is done, I go home, and then another lumberjack comes up and does the work. So this is not what we want. This is not effective. We want to go, well, where we want to end up is something like this. We want to say, okay, the thread should not be our unit of work. That should not be the finest level that we work on. We want some abstraction below the thread level. Our unit of work should be the task, this log of wood. This is the task we work on. And the thread should be like a worker that works on a number of tasks, not just one. So ideally, to have no context switching at all and to have the maximum efficiency, we want a worker to have the same chainsaw all the time. And so we can just you can just work on one log after the other. Or, of course, I'm still talking about computers. So what we want is thread locality. Ideally, we want one thread to run on one core all the time. That will probably not happen most of the time, but that's our ideal scenario. Then we can leverage modern hardware. Then we can leverage the fact that the CPU will load lots of stuff in its cache, that will try to predictively execute stuff. That will be, it will do pipelining, things like that. All of these optimizations that modern CPUs have get lost when we overdo the context switching, because it's like a restart of the whole scenario over and over again. So enough with the lumberjacks. Oh, actually, they're going to come up again later. But on a sort of more serious level, we want, well, I think there isn't really an established term for that. I tend to say task because I saw it somewhere in some, I don't know, some online course or so. But there's not really an established word for it for the sub-thread level concurrency. I'm going to show some terms later. So what we want is we don't want just the thread level. We don't just want processes where one process has a lot of threads. We want processes, of course, processes that have many threads, but we're going to consider these threads as workers. And each of these workers should have many tasks. And a similar, or the approach is also known as the reactor pattern, where tasks are, what did they say, they're demultiplexed on the workers. So we want this, we want sub-thread level concurrency. And another point that is very closely related to this efficiency thing is asynchronicity. Maybe some of you have seen the talk this morning about async, everything async. I forgot the title, but how it, again, the hardware we use offers us a lot of power in terms of doing things outside of the CPU. Basically, when you do some I/O, you don't need the CPU for that. But the traditional model we use, if we use the Servlet API, for example, and do a database access or network access synchronous file I/O, will block the current thread. It will not block the CPU. That's fine. We're not producing CPU load. But the thread will be there and will have a certain blocked state. Will be waiting or actually blocked or so another thread. Well, let's say it's waiting. IO weight, whatever. So in a synchronous model, where we hear, and this is not a sequence, I'm saying requests here, 10 requests, and then our threads, our workers, but it's not a sequence of threads coming in over a certain amount of time. This is a snapshot. We're looking at a system, and at this point in time, it has 10 concurrent threads, and 10 requests that are being worked on in parallel. And each of these requests has been assigned a thread. That's a traditional thread per request model that we have in Java EE, in the Servlet API, for example. Now, if I do blocking IO, what do I block? I don't block the task, right? I block the worker, because the threads are still our worker pool. We use the threads to actually do the work. So if we block, we block the worker, we block the lumberjack. In this case, that will affect one request, right? Because each of the requests has one thread to it. If this thread is blocked, then this request is not being worked on. But in this task model, where I said, okay, we want many tasks to be worked on by a worker. And that's probably really many. If we really want, so we want to keep the number of threads low. Let's say we have an 8-core CPU, and we just use 8 threads in our worker pool to work on incoming requests. So we have 1 thread per core. But we want to work on thousands of requests, so it might be 1,000 tasks that one worker is working on. So if we now block the worker with blocking IO, then we block many tasks. Actually, not 3 or 4 like drawn here, but it could be 1,000. Oh well, it's open-ended, obviously. So I hope you can follow this train of thought. We want sub-level concurrency. We want a finer granularity. We want tasks, but of course we still use threads as a pool of workers. So we can't block. We can never block. We must not block our worker pool threads that work on these tasks. Don't worry too much about it, because you don't have to implement this. It's been done, but you have to know about this. So I said one of the main problems with threads is the efficiency, and this has actually been solved. The idea is I go sub-thread, I have sub-thread concurrency, I have a task-level concurrency, and I use asynchronous IO to never block my worker threads. I'm going to show you 4 different, this is really irritating, I'm going to show you 4 different models, 4 different concurrency models, and they are not different in this way. All of the models we're going to look at share these characteristics. They all implement sub-thread level concurrency, and they all encourage asynchronous IO. And also, if you see somebody saying, this is a reactive system, this is reactive, this follows the reactive manifesto, all of the systems that I know that are reactive also follow these principles. That does not mean that by doing this, you're automatically reactive, but to be reactive, you have to follow this. So problem 1 is solved, and we're going to look at how the different models solve it. The second problem is the programming model. The way threads communicate with each other, the way we compose our programs out of threads. It's basically, the idea is imperative programming. We call methods, we create a new, it's object-oriented, we create an instance of a thread, we call one method on it, we override stuff, and then something is calculated and it has to be put somewhere. And it's usually in some variable that can be accessed by multiple threads, what we call shared mutable state. If you see shared mutable state somewhere, that's usually bad. If you have to protect it. If you don't protect your shared state, you will have racing conditions. We saw threads can be executed in all sorts of fashions in different orders. So if they just write in something, you will get a big mess. You will have errors, and it will be because they're kind of non-deterministic, because it depends on the execution order of the threads. It will be difficult to find out where the error actually came from. So what was his name again? Mr. Lee, as Mr. Lee put it in his nice paper. Oh, well, there were many publications, I think, about threads and why they're not a good idea or not a good idea anymore, or not a good idea for an application programmer, but rather something low level. And he says, well, the one beautiful characteristic of programming languages is that it's so deterministic that we can say these are the steps that are executed and the outcome is clear and we can reason about that. And with threads, we give this all up because we have no idea in what order it's executed, and we can't. So what we do is we introduce locks and synchronization. So we protect our shared mutable state, but that, of course, leads to contention. If I have many threads that want to write to the same area in memory, then they will queue up. I will have contention that will hit my performance. So luckily, I'm not the only one saying this, or many people are saying this, but even this JVM architect, John Rose, is saying this. He said, I think in February this year, threads are passé, which is, they're not going to go away, but we need an abstraction on top of threads, something that's easier to handle. He says, yeah, it's an old model. 15 years ago, it seemed like a good idea, but the mechanisms we have, it's just not a good fit for modern hardware. This is related to the context switching and non-uniform memory access characteristics that just make it inefficient to switch between too many threads. Also, threads are kind of heavyweight. When I create a thread on the JVM, probably a few of you know that there's the default, there's a parameter, the XSS, I think it is, the stack size, you can configure that. And the default stack size, that's memory, that is reserved for the call stack of a thread. The default stack size, stack memory size on a 64-bit JVM is 1 megabyte. So we're talking about systems here where we want 10,000 threads, so that's 10 gigabyte of memory for my thread stacks. That's in addition to your heap space. So it's not a really lightweight model. And the synchronization, this whole locking thing just doesn't work out. So when we talk about this, I already said, okay, we want to go subthread and we want to use asynchronous I/O. When we talk about programming models and we talk about asynchronous, we also have to talk about how do we use asynchronous APIs. What's the standard way of using an asynchronous API? It's the callback. I call something, and I say, when you are done, I'm just not going to care. I'm just going to send you something here. Please open this file, but I'm not going to wait for you to open this file. When you have opened this file, then please invoke this function or this method here. And then I can add the numbers. I think this is JavaScript, right? This is actually just pasted from somewhere, copied and pasted from somewhere. So it opens a file, and then on the file open, there's a callback. When the file is there, then it will go over the lines, and there's another callback then to write the file. This is not very readable code. Callbacks are a bit of a pain. So when we look at different programming models, we're also going to look at how do they communicate? How do the entities in these models communicate with each other? What is their model as opposed to callbacks? And also, how can I use asynchronous APIs? Is there a nice way to use callbacks, something on top of that, or some alternative to that? And I might also be in a position where I have to use a synchronous API. I just had 3 slides ago, never block, never, but you know, for every rule there are exceptions. You might be in a situation where there's just no alternative. The most prominent example probably being JDBC. If you want to use a JDBC driver to connect the database, you'll have a very hard time to make that like an asynchronous call. So we're also going to look at these different toolkits and see how can I deal with the synchronous APIs. So just to be fair, callbacks, I don't like callbacks, but of course I am aware of the fact that this could have been written in a different way. Different languages have different syntactic sugar for callbacks. You could say, oh yeah, why doesn't he use scalar futures and he can have nice for expressions around them? Or even in JavaScript, there's the promises, and I can say do this, and then do this, and then do this, and it looks like sequential code, but it's actually async. Just like async await, if you've used C#, or if you've it's also in Scala, it looks like sequential code. You say async, and then await this, and it's actually asynchronous, and the code is going to be invoked when the async stuff is finished. So this can all be done, sure, but it's syntactic sugar. It doesn't solve some problems of the callbacks, because in this, a callback might be okay if you have one function, and when the event's done, you want to invoke the next and then the next, but often you don't have this sequential chain of just one function after the other. You might want to spread work out. You might want to sort of wait on something to happen, and then you want to invoke 3 other functions, or you want to wait for 3 functions to be completed, or you want to wait for the first one of 3 to be completed, and things like that. So although there is syntactic sugar for callbacks, it's still callbacks, and we at least want to explore if there are not better possibilities for that. So now, this was all the sort of the build-up. why we don't want to use threads. Now we're actually going to look at some models and at some code too. If you're scared of code, it's yeah, you're going to have a hard time. But what are we going to look at? If we look at different concurrency models, what are our criteria? So from what we said now, from what we don't like about threads, you can say we want predictability. So we want to look at, does this programming model give me a different approach of thinking about my program, rather than having to think of something is happening at the side at the same time in some way? Does it have a different approach to that? I want to look at composition in the sense of how do my asynchronous units of work, how can I combine them? And I want to look at integration in the sense of how can I use asynchronous APIs, how can I use synchronous APIs? And is there another one? Oh, and state, of course. I said something about shared mutable state, that we don't want to have that. But of course, we're not always stateless, right? Not every program is purely functional and has no internal state. It's very likely that at some point you have some state that you have to handle in memory in your program. So if we don't want shared mutable state and we don't want this synchronization and locks and stuff, how do these models actually handle state? So the 4 models we're going to look at are, the first one is Fibres. The library is called Fibres, and I said there's no term has really emerged for this subthread level concurrency, what I call the task. So some people call it coroutines, especially to express the notion that it's actually collaborative multitasking and not scheduled by the operating system. In Go, of course, they're called Go routines, which is a little play, of course, on coroutines. Some people say it's just green threads, like the first versions of the JVM, or I think in Ruby you also have that. It's like threads, but it's not operating. It's not native threads. We just have JVM internal threads. In the Clojure world, they're called inversion of control threads, I think, or some people call them that, to express the fact that they actually use this to get around callbacks. Some people say user mode threads. The Fibres guys say, the guys who do the Fibres actually say it's user mode threads. So if you see any of these terms, there's a certain likelihood that they're talking about the same thing, what I call tasks. Channels, of course, yeah, we're going to look at this, so I'm not going to talk so much about that now, but these are the different models we're going to look at, and the first one is Fibres. And this is probably, I would guess not many people have used this here. It's, I think it's not so popular. What is a fiber? It's pretty much like a thread, right? I just create a new fiber, and I have this one method that I have to override. And in the spirit of duck typing, we could say it looks like a thread, it walks like a thread, it talks like a thread, it's probably a thread. And in fact, you use it like a thread. I said we have this little example. I have some example code. So the example we have is, it's a lookup. I want to look up a word. I hear a word that I don't understand. I'm not a native English speaker, and people might throw things at me and say, you are a doofus. And I want to know what does it mean, so I look it up on Wiktionary, on the Merriam-Webster dictionary, and on the Urban Dictionary, because it might be a slang term. And I want to do this in parallel. I want to do, I take this word, I want to do 3 HTTP requests in parallel. I want to aggregate the results, and then when all the 3 are done, I want to see the results. So I have the code on my machine, but the whole switching thing, we can do, if we have some time in the end. Not that it's very exciting, but I could show the code so you would see it's that these models actually do something. The funny thing here is, if you look at this, I said it looks like a thread. It does. It's not. It is. What it does is it uses bytecode instrumentation to detect these at startup time, and will actually have its own scheduler to run many fibers on the thread. What's interesting about this code is that it also looks like imperative code that we write in the thread. For example, this HTTP client. This is the interface is a regular Apache. Oh no, what is it? NGNG. Async HTTP client, I think. But this one, the closable HTTP client interface is even, I think, some standard from Apache HTTP also. But the interesting bit here is the Fiber HTTP client builder. So I get an HTTP client that I can use in a synchronous manner. When you look here, I just do a response equals client execute. There's no callback there, there's no async, no asynchronous messaging, whatever. So what it does is, this Fiber HTTP client builder gives me a blocking API, but it does not block the thread. It's only fiber blocking. So this is actually a smart thing. They give you some additional APIs. They give you some utilities that give you asynchronous, that give you synchronous APIs on top of asynchronous APIs. So you can basically program like you used to program in Java. You don't have to, the mental switch is very, very small. Some things you have to keep in mind, like you can't block the thread, or you shouldn't. And there are some extra features. But basically, it's like multi-threaded programming. So it looks like blocking, and it is blocking, but it's only fiber blocking. It doesn't block the thread, which is a good thing. But in the end, you have to aggregate the results somehow. So at the end, I just call a method where I put in the result, and that's going to write in some variable that will live for the runtime of the program. So that's this shared mutable state thing, right? This is something that would have to be synchronized, or I would have to use a data structure that is thread safe, because my different HTTP results will come in concurrently and will all write to this, this space in memory, basically. So when I want to aggregate the results, I have this, I use a concurrent hash map here just because it's thread safe, obviously. And to start my parallel retrieval of my definitions, I start the fibers like I would start threads. So the retrieve info was my fiber. So I just say a new retrieve info. Oh, this is the key. The key, I think, is the name of the website. So at the end, I can still make the connection between the website I'm looking up and the definition, and my search term, of course. And the sources is just a list of the URLs per key. So it looks very much like multi-threading. And in the end, it's about, I have the sub-thread level concurrency, but I still have shared mutable state. It's not really a different programming model in terms of the approach. So the major advantage, you could say, of the fibers is it's just like thread-based programming. If I'm used to that, I don't have to learn something new. The main disadvantage, though, it's just like thread-based programming. All of the disadvantages we have in the programming model, and that is not having a sane way of thinking about the code and not having a sane way of dealing with mutable state, we preserve this, we take this with us. This is how it works with the idea behind this HTTP client, for example, what they offer, and I have to give it to them. They have some nice things there in the drawer. They have the idea of this fiber async that actually does what we saw with the HTTP client. This wraps an async call that takes a callback, right? It will take something where you can actually put in a callback and have a completed method, and we'll wrap this in something that looks like a synchronous call. But as I said, the idea or the funny thing behind it is it will block. It will be a blocking call, but it will not block the thread. It will only block the fiber. And that's about all there's to say about fibers. They're like threads, but just much more lightweight. You can actually, there's something you can easily try if you run a program that creates thousands of threads. For example, on my MacBook, if I run a program that attempts to run 10,000 threads, it will just crash at about 2,000 or so. Well, this is actually, I think, an operating system limit. Maybe it can be configured, but standard-wise, at 2,048 threads or so, it will just crash. The JVM will crash and will say, I cannot allocate more native threads. If you use fibers or any of the other things we're going to look at, you can easily create 100,000 fibers or more, probably. I haven't gone up higher, but they're really lightweight. So you can actually, so the efficiency problem is actually solved with it. You can have 10,000 connections, if you will, and each connection can have its own fiber, or 10,000 events, or whatever you have, and you can use this programming model. It is thread-like. It has some nice tricks. As I said, it works with instrumentation, so you have to add a little jar to your JVM options. You have to say JVM options agent something something, and add this fiber jar, and then it will, so at startup time, it will detect the fibers and it will instrument the bytecode and put in this mechanism. and has something like a suspendable annotation because they are coroutines. The operating system scheduler will not switch between fibers. You have to let go. You have to make an async call, or you have to stop your work for other fibers to be able to take over. They have an annotation suspendable where you can say on a method, okay, this is a suspension point. You can reschedule this fiber at this point. So you give back control to the scheduler. It works nicely with threads as well. You can still create new threads. They have a common abstraction on threads and fibers. So you can program things that take, it's called a strand, that work on threads or fibers. You can use things like thread local. Some people are used to using thread locals, which is of course a problem if you use sub-thread concurrency, because it's not really local anymore then, is it? If one thread works on 10,000 events, then its local environment is global for these 10,000 events. So a thread local might not do what you want it to do in a sub-thread level concurrency world, but it works with fibers. Fibers alone, I think, are a bit low level. It doesn't really give you a new programming model. It's almost a drop-in replacement for threads. So some things you need to learn. If this is what you're looking for, if you say threads are great, they're just too heavy, then fibers might be good for you. The English Channel, the White Cliffs of Dover. So the next thing is channels. That's getting more interesting in terms of concepts. This is actually a different way of communicating between asynchronous routines. Channels go back way to 1978, and I think it was, the paper is this, that about communicating sequential processes. Where there's a whole theory behind it, and a lot of mathematics and algebra about what works and how it works and why it works and what the laws are of it. But as I said, I'm very pragmatic. To me, it's more interesting how it works in code. But it obviously works. It's very popular in Go. It's the standard model of concurrency in Go. In Go, you have Go routines and channels. And somebody in the Clojure world, which Huehnken took basically the Go functionality and said, let's put this into Clojure, and created Core Async, a concurrency library for Clojure, which is a Lisp-like, scheme-like language, as you probably know, on the JVM. And he brought Go routines, and now they're called Go blocks in Clojure, and channels to Clojure, and some nice syntax or operators with it. So what happens here? So this is, we define a channel, and here we define a Go block. So a Go block is a lightweight asynchronous thing. It's like a fiber, really. It's not a thread. There's another expression that starts with thread, another function thread, that will create a new thread. But here we say we want to create an asynchronous routine, but it shouldn't have its own thread. And we say, okay, in this Go block, what's supposed to happen? We just want to print something, and the parameter, well, you know the parameter for println is a string, right? And here, but you say, okay, instead, again, I pass a function here, and the function's name is this. You can, if you have any good ideas how to pronounce this, but it's basically a take out of the channel. And of course, the parameter is the channel. So I say print the result of this operation, and the operation is take something out of the channel. Again, this is a blocking operation, right? It's not, it takes something out of the channel. So the channel is empty, it's going to wait there, it's going to block. But again, it's not going to block the thread, it's going to block the fiber. And here we put something on the channel. And this is, we're not in a Go block here. It's a subtle difference. So if it's actually about the thread, we use the 2 dashes here, not 1. But that's actually of no importance at all for us now. But I think the basic principle is probably clear. We decouple the one execution from the other by putting something on a channel. We say, listen basically to this channel, and then I put something in and then execute this. It's not a bus though. A channel, it's just a decoupling. This channel just takes this one element and it kind of synchronizes things. It's not an asynchronous model per se. I can make it asynchronous, more asynchronous, by turning the channel into a buffer and say I take a channel with 2 elements. Then I can put, in this case, 2 things in the channel, and then it will block again until I take something out. But of course, I can make the channels much bigger than 2. So the idea here is I say it's a buffer channel, so the things can actually sort of be decoupled again from the producing of output can be decoupled from the consuming of input, and I can put stuff on the channel. Oh, this was only the one bubble there. And this way I can already have some asynchronicity, or if I combine this with the Go blocks. Let's look at our example again. So if I want to get results from websites and want to aggregate them, and I can use channels for this. So we define let's look at this first. So we say we want to get a URL, and then, again, this uses a callback. So the way we can deal with callbacks is here that we put in a channel instead of a callback, or as the callback function, we put it on the channel function. So we move from callbacks to channels here. So this function actually expects a callback. It's like if I make an HTTP request, and then when the result comes back, I want to execute something, pretty much like like an async HTTP client in Java would also do, and put in the function here. And the function that's going to be executed, again, asynchronously in a Go block, is put something in this channel that I have passed earlier as a parameter. And what I want to put in is the body of the HTTP response. So now I use this to call 3 websites in parallel, and all of the responses are going to be put on this channel. And then I have this Go block that will just it will go through the loop every time something is on the channel, because it will block here, right? It will recursively call itself, but at this point, if nothing is on the channel, it will just block. But again, so I don't know, it seems a bit repetitive to me to say it over and over again, but I just have to say it again. When I say blocking, it's not bad in this case, it just blocks the Go block, not the thread. So that's how it works. And here, of course, this is very simple code. I didn't even write that, thanks to VJ. When it has 3 values, when it has aggregated 3 values, because we know it's 3 websites we're querying here, it will just return this, and then this println will get the values and will print it out. So what we did here is we defined a channel, again, a buffer. We can take a couple of responses there to have it nicely async. We will aggregate the results recursively by here, sort of blockingly waiting on something coming from the channel, and then just put it back into this function. So it's a nice way of kind of, the state is basically, the state in this application is handled in the channel. Right? We don't have a variable where we aggregate the state. We don't have shared mutable state. We have a stateless function that loops over this channel. So the channel becomes our keeper of state. That's actually pretty smart. So I think it has some very nice ideas. It's obviously, if it's very popular in the Go world, as I said, it's a working model. But also, it's about, this whole thing is about exploring things on the JVM, right? Thinking about concurrency and exploring what models we have and what's there and what are the ideas behind that. So here the focus, of course, is on a nice composition model that I can say, I put something on the channel, somebody else takes it out of the channel. So it's more, I don't think of programming as function composition or method invocation, definitely not a sequential sort of imperative style. Maybe, and even a functional style will not naturally be asynchronous, right? But this is more a flow style. I put something on a channel, and this might trigger something else. It actually has a lot of nice options too. I can listen to a couple of channels. I can select from channels with the else statement. So I could start these 3 and then say just continue with the first one that's finished. Things like that. It gives me sanity in terms of predictability on when I reason about my code, because a message comes in, and then this is, as I said, it's a blocking operation, right? It kind of synchronizes on the queue, on the channel. So it takes one message out of the channel, and the code will be executed. And when that's done, it's going to take the next message. But it's not going to take 2 messages in parallel, and we don't have this weird thread parallel execution. We have our different blocks that listen to different channels and do different things. Of course, this can all be, the requests can run in parallel, and then the other things can run in parallel. But we don't have this weird situation where it's a bit unclear what the state of something is or who's just accessing it. It kind of sequentializes, I don't know the word for that, our message processing. We saw the Go. I think it's a macro. We saw the Go macro that will create the subroutine, the fiber-like subroutine, the coroutine, whatever you want to call it, the Go block. And there's another one, thread. So you can do the same thing with threads. So I said never block, and that means that your main worker pool must never be blocked. But you can use this to offload work to a separate thread. If you want to use a synchronous API, you can use a thread and say, I'm going to create an additional thread to work on that and not contaminate your worker pool, if you will. And to a certain degree, channels can be seen as the keepers of state. You have many opportunities now to keep the mutable state out of your application by aggregating it in channels. But let's move on. Event loop. If anybody has worked with Node.js, then that's a very familiar paradigm. The idea is, well, I consider everything coming in as an event, and I register event handlers that will react to that. The event is put on a bus, and the loop works on this bus, or a couple of loops, and this will trigger event handlers to be executed. So it's a bit like Node.js, but it uses multiple threads. Node.js, the main event loop in Node.js just uses one thread, as far as I know. In the Vertex, it's actually going to use multiple threads. Vertex is our example here for the event loop model. One thing that's funny about Vertex, that's independent of concurrency, is that it allows you to use any JVM language, really. What you do is you deploy little units called verticles, and you can write these verticles in Clojure, in Java, in Scala, in JRuby, I think, probably Python, definitely JavaScript. So it's very polyglot. Some people like that. And the way they communicate is usually a JSON. What does a vertical look like? It looks like this. So I have a class that I have to inherit from, and then I register myself on the event bus. I get this event bus. So this is like a global. Okay, in the abstract vertical, the vertex is available to me as a member, and there are static utility methods to access the environment. It comes with some infrastructure too, right? It's not just maybe it goes a bit beyond channels because it's like a runtime, if you will. And then you register yourself and you say, okay, this is the address. I'm going to be known as ping address. And somebody's going to put a message on the event bus and is going to say this one is for ping address, and then this is going to be invoked, especially this lambda here. So again, callback style. Obviously, this is like a go to world example. I get a ping, and I'm going to reply with a pong. Let's look at our example. I want to have 3 in parallel. I want to have 3 verticals running that fetch the URLs, and I want to aggregate the results. So this is our actual vertical that will do the HTTP request. And again, it's interesting what they offer as a utility library. We saw this in the fibers with the fiber blocking HTTP request. But here, well, again, we register as a consumer, so I have to put a message on the bus saying this is a message for definer task. And this is the Vertex HTTP client that takes a callback again. And when I get the response, I'm going to take the result and going to put this on the event bus again, because this is now the way we communicate, right? I don't invoke. There's no callback that has been passed to me that I could invoke, or there's no channel. I put things on the bus. I don't even know who's going to get it, right? It's the utility, that's interesting, the utility APIs that you get with Vertex, they're very callback heavy. So you can really feel that it's kind of following the node approach. You don't have to use the event bus as much. You could actually you can do a lot just with callbacks if you prefer that style. But there are, of course, there are advantages to using the bus. But I think the general principle is probably rather easy. Again, this is the creator of our task. We have to deploy the verticals, right? We have to tell Vertex, create these verticals that we want to use to get the HTTP responses. So this is the static utility method I talked about. You get the Vertex runtime, you get the event bus. When you want to deploy verticals, you can actually pass a couple of options. In this case, I just say, okay, I want to deploy 3 instances. I don't want to deploy 1 vertical. I want to deploy 3 verticals because I want them to run in parallel. And then I just deploy them, and then I send this. Oh yeah, once they're done, when the vertex is done with the deploying, it will again invoke a callback, and I can send the message here. This is usually JSON. I create a JSON object here, And then I sent this to definer task. And then, that's interesting. That's kind of, now I have created 3 verticals that are all called definer task. They all have the same address. Now I put something on the bus for a definer task. Which one of my tasks is actually going to get it? Where's it going to end up? I don't know. And the Vertex won't tell me. It's by default, it's going to use a round, it's called a non-strict round robin. So it's kind of conveniently trying to round robin the messages. So it's actually most likely each of my verticals are going to get one message, and it's actually going to be done in parallel. I could do it differently. I could get the identities, or I could configure them. I could generate a name and call them task 1, task 2, task 3, and configure them when I deploy them to have this name to listen to that address. But it's actually a very common pattern to say, I want to use this. I want to use this for scaling. I want to use this for parallelizing things. I just put multiple verticals on the same address, and I have automatic load balancing around that, automatic round robin load balancing over my verticals. So that's why I chose this for this example. In the end, we saw the vertical sends the message on the bus. So I need another vertical that collects the results. And here I chose to make it stateful. So this is something you have to sort of, Vertex doesn't give you this automatically. By the vertical, just by looking at the name of the vertical, you can't say, oh, this is stateful, this is stateless. So here, the identity is actually important to me. I encapsulate state in the vertical. So if I want to send a message, I want to make sure it actually goes to this specific vertical. In this case, this is solved by just deploying it once. I take the collector, and it's just going to be deployed once. So that's not going to be a problem. But so we encapsulate the state here in the vertical, and that's a legitimate approach. That's if you want to handle mutable state in Vertex, either you encapsulate it in a vertical, or you kind of break out of the whole Vertex system altogether and just reference some globally visible data structure somewhere, which is of course even worse. So, the other one's not bad, so that's worse. This is good. You encapsulate it in a vertical, but then you actually need the identity of the vertical, obviously. Another nice thing about Vertex is this, what they call the hybrid thread model. So it actually gives you a concept of background workers. I said in Clojure we have the threads and the Go blocks. So you want to offload synchronous work or CPU-bound work to another thread pool. In Vertex, they've actually implemented this through types. You can have worker vehicles, and these vehicles will be worker verticals, and these workers will be executed on a different thread pool. So you have your event loops, which is already multiple threads that work on the event bus. Now you have a long-running or synchronous thing. You can say, oh, this is actually a worker vertical. I don't want it to spoil my event loops here, so it's going to be executed on a different thread. So there were a lot of interesting concepts in this. It's very loose coupling. I just put messages on a bus, and these messages are going to be picked up by some event handlers. This, in terms of reasoning about my code and what's being executed in what order or how my code is executed, again, it sequentializes it for me and gives me the sanity back, the predictability back. I get the event, and then my code is executed, and it's a so-called single-thread illusion. At this point, I just have to care about this one thread that my vertical is running on. There's not going to be any sharing of a vertical of multiple threads at the same time. So I can use things, I can encapsulate state in there, things like that. The hybrid thread model allows easy integration of synchronous APIs. If it comes to async, it's usually callbacks. It's very callback heavy. It's not my taste, but well, other people might like it. And we already saw there is, of course, syntactic sugar for that. State handling, encapsulating state and verticals, needs some care. You have to be aware of the identities of the verticals, or if they're sort of not to be identified, and you just use it as a general address for load balancing. And this is, in this example, there wasn't room for this, but something you get with it is distribution, because Vertex, this event bus, you can actually run it in the network. And this is actually a very powerful feature, because you have a unified model now. You don't have to, if you do thread-based programming, you're going to have multi-threading in your local environment, and then you want to go across the network to another machine, you have to use something else. You have to use messaging, or you have to use a REST call, HTTP, RPC, or what have you. So usually we have different models for distributing work locally and distributing work over the network. With an event bus like this, it's a unified model. So you can build your application in this way, and if you want to scale out, you just add another machine to your event bus and deploy the verticals there, and can sort of spread your system over a number of machines without having to care much about it. I think that's this is a very strong feature of Vertex, of course. Actually, a feature it shares with actors, the last of the four approaches I want to present. So, actors. Also, there's a good theoretical foundation for that. It's even older than the communicating sequential processes. It's from 1973, from Carl Hewitt. And he says, and I have to read this for me because I don't know by heart, the actor model is a model that treats actors as the universal primitives of concurrent computation. That's a bit like in object orientation. We consider objects the universal primitives of our computation. Everything is an object, right? All the way down until it's turtles. But so I get a message. I can make local decisions. I can change my state. I can create new actors. I can send other messages. And I can change my behavior. That's an interesting part, but we're not going to go into that too deeply. But compare it with object orientation. In the object-oriented idea, a method is invoked, as also often described as getting a message. Objects send messages to each other. So you receive messages, you can change your internal state, you can send messages to other objects, you can create new objects, or maybe destroy them. So it's kind of similar, but actors, of course, all communication with actors is asynchronous. The way it works is when you create an actor, you don't get a pointer to the actor. You say, system, give me an actor, and then you get a so-called actor reference, an actor ref, and that points to the actor's mailbox. Like a channel, every actor has its own mailbox, or every actor has its own mailbox that is a bit like a channel in CSP. And the asynchronous part is the sender sends the message to the actor reference, the actor ref, and the message is going to be put in the mailbox, and this is one thread, and at this point the sending thread is done. The message is in the mailbox, and yeah, we don't know about anything else. And then there's a so-called dispatcher, which is a thread pool, and so the manager of the mailbox, if you will. And this dispatcher will be notified when something's in the mailbox. It will dequeue the message from the mailbox and invoke the actor. So again, a bit like with channels or with events, this asynchronous messaging is obviously a principle that has some universal appeal. So you put something in the mailbox, you're done, another thread from another thread pool or from wherever will pick up the message, will actually invoke the actor, and will work on that. How does this work in practice? It sounds interesting. It's often confused. People see this and think, oh yeah, messaging, I've seen messaging, that's like JMS messaging or RabbitMQ or whatever. But here, as we said earlier, it's our principal model, it's our primitive for the computation. So we do everything in actors. It's very lightweight. It's just putting something like in the Java, basically a queue, and it's all local, possibly. What does it look like? So I have to create an actor. This is again, remember the example, I start something, I want to spread it out, I say I want a definition for this term, I spread it out, I do 3 HTTP requests, and then I want to collect the results. So here we have 2 actors, we have a coordinator that will spawn the child actors that will do the HTTP requests, and will also itself receive the results, and it will collect the results here. Again, we encapsulate state in something else, not in a vertical in this case, but in an actor. And here so this is the receive block. An actor gets messages. We saw that, and the dispatcher will call the actor and give it the message. But in the actor, this is Scala code. I hope it's just more concise than the Java version, so it's simpler. So in the receive, we have different commands. Either I get the start command that gets me going. The start command will have me create the other actors. So I have a list of websites I want to query. That's the sources. I have a list of sources. Each of the sources contains a key and a URL. So for each of these sources, I create a new actor. I initialize this actor with the key and the reference to this coordinator. Self is myself. It's like a this. But you can't use this because, you know, we don't work with references here, we work with mailboxes. So self is my actor ref. Self points to my mailbox. Well, not to my, but to the coordinator's mailbox. And it sends a command to the child actor. It creates a child actor here, initializes it with a reference to itself, and sends it a command. Then, just for fun, it also schedules a message. So if it takes more than 5 seconds, it will actually get a message and say, cut it short. And if it receives a result, that will probably be from one of these sub-actors here, from the children, it will just add the results to the map here. And at the end, it will send a message to itself and say, okay, oh, I had 3 sources, I received 3 results, so just send itself a done message. And then in done, it knows it's done, so it could close the system down and print out the results or whatever. Does that make sense? So the child actor is also super simple. Again, a receive block. We saw this message here. This message is something we got from the coordinator. So the coordinator started this child actor and sent this command here, send get a definition. So, oh, again, this is this topic about asynchronous APIs. Again, we have an HTTP API here that is callback based. Or in this case, I think we get a future back, a Scala future, which is, as I said earlier, syntactic sugar for a callback based API. But the actors have a nice mechanism to deal with this. You can say, take this and instead of putting in another function that's going to be executed as a callback, I say pipe to myself. So what that's going to do is it's going to put in a function that will sort of, when the HTTP request is completed and the onComplete handler is executed, it will take the result and wrap it in a message again. Or actually, it will not wrap it in a message. It will just take the result and send it as a message again to myself. In this case, the message is going to be an HTTP response. So I just, in my receive block, I also say, okay, I can also receive HTTP responses. So this is the one that's going to come from here. And in this case, I'm just going to take the body of the HTTP response and send it back to the coordinator. Because when I was initialized, the coordinator passed his reference to me here, this actor ref, I can just use that. And then, okay, there's some error, actually there's no error handling, but in theory, you could build in some error handling as well. So you see, again, this is a very, again, this gives me some sanity back. It's not weird things happening in parallel. I get a message, something happens, some other message is sent, right? It's asynchronous, but when it comes to processing a single message, it's super simple, right? So it's a bit of a stretch that it's, of course, it's still difficult to reason about a complicated system. If you have a big system and a lot of messages are sent and you have to follow the flow of messages, then you might still have some difficulties. But when it comes to the single, your single unit of code, you don't have to worry about your code being executed in parallel by different threads and of things having to be synchronized or locked using locks and things like that. So it's again, we get some sanity back. So we just send the result to the aggregator. And another little bonus we get here, you saw, if you remember, that in the coordinator, when it got the start command, it would create the task actors as child actors. And actors form a hierarchy. If I create an actor, I become the supervisor of the actor. So the first actor we created, we said a system actor of coordinator. So that was, there's the user actor at the top here, the system actor, well, the guardian actor, we say. And that will be the supervisor. But then when I create sub-actors, like the tasks I created, I'll be the supervisor. That means if something happens in the task, I can be notified. If an exception is thrown, although this exception is thrown on a completely different thread, and usually I would not be concerned with a stack trace at all or anything, I can actually convert this into a handler being called on the supervisor. So it gives me very fine-grained and very flexible error handling. In this case, yeah, you could just retry the HTTP call or well, depending maybe on what the error is. So, summarizing, actors, again, like I think like all the approaches except Fibres, it kind of sequentializes things. It's events or messages or whatever. In this case, it's messages. It gives me this predictability back when it comes to one message. It's messages, it's not events. That was probably a bit too quick to sort of see it in detail, but if you remember the event bus, we would put something on the event bus with an address, but it's on the bus. The receiver is the bus, and we just kind of put a label on it. And we're not really sure what picks it up. And it can be, we don't even know who picked it up if we have multiple verticals with the same address, because it's going to be routed. In actors, it's messages in the sense of there's always a receiver. I send the message to somebody. I don't just put it out there on the bus. It's not out of my control who gets the message, because somebody listens to these events. I control who gets the message. In terms of the actor ref, when it comes to what is after the actor ref, there can still be some routing going on and things like that, but that's necessary, of course, for scaling. But it's a slightly different thinking. I say, this is the coordinator, I want to send it back to the coordinator. I need the coordinator to give me a reference first, so I can send something back to the coordinator, while in an event bus, we'll just create an event and put it on the bus. There are nice tools to integrate with asynchronous APIs, namely the pipe tool, and if you have the other way around, if you have an actor and you want a callback, you can use the ask pattern. For synchronous APIs, we saw the dispatcher that is dispatching messages and invoking the actors. You can define different ones. And you have, as a bonus, again, it's distributed. It's a unified model for local and distributed. And you have supervision as an extra for error handling. So if we look back at the models we explored here, maybe it made sense in terms of it's a story that builds up. We looked at Fibres, which is a very simple approach, which gives us the efficiency and the subthread level concurrency, but basically that's all we get. Then we looked at the channels that gave us a new way of composing things and of interacting between asynchronous code. So on top of the subthread level concurrency, it added, time's up, it added asynchronous messaging. Vert.x, as a bonus, gives us a unified model for distribution and local concurrency. And Akka has all this and also gives us a special way of supervising things with the supervisor hierarchy. So, to summarize, I think concurrency is interesting, and I hope you feel this too, and maybe got some ideas of what to look at and what to explore, or what to discuss over a beer when it comes to new concurrency models for the JVM. Threads are old, we don't want that anymore. They're not going to go away, but they're not going to be the user-level API. They're not going to be the application developer's API. We need an abstraction on top of that to work with. We need event buses or actors or fibers or channels, something that gives us a sane way to think about our code. And luckily, on the JVM, alternatives are available today. They're all production ready and nice and good. I personally like Akka a lot. So if you don't have the time to look at all 4 or 3 or what others there are, I think Akka is kind of, it's so mind-boggling too, because this whole messaging approach is so different from the way we're used to program that I think it's a very inspiring thing to look at. I think that's about it. Oh yeah, and there's, if you're like me and you like books and you want to read a printed book, I highly recommend this book. It's called, obviously, 7 concurrency models in 7 weeks. It covers all the concurrency models I talked about and 3 more. But it's not restricted to the JVM. It also looks at other runtimes, of course. And that's it. If there are any, we don't really have time, but if there's any pressing questions, or maybe you just come down and ask me in person if you have any questions, so we can get set up for the next speaker.